9.2 is about fluid pressure and depth. Okay? Pressure and depth. When you dive down to the bottom of a pool or ocean, we've talked about this already, you feel that pressure on your ears. Okay, if you've gone scuba diving before. Has anyone gone scuba diving in here? No. Do you notice the pressure when you get lower in the water, obviously? Yeah. You feel it on your body. Now.
You don't have to go scuba diving to feel pressure.
Wait, did you see that guy that went like free diving in one of those like hole things and went down like all the way, and then when like you like came back up, you have to like answer like a bunch of questions.
Oh, because you can get the bends.
No, yeah. No.
But if you're just like in a
Gas gets released from the chemical reactions in your blood when you decrease in pressure too quick, and what will happen is your body will actually like kind of inflate and stuff. The bends is usually, I think, right for your, isn't it like really bad pains and it could kill you and stuff?
Did you see the guy that like exploded when he came up?
No, he was like trying to beat the.
How would you die? What would happen? Your heart would stop, or?
Did you see the guy that like exploded?
All he had to point out the answer yes.
But I mean, Mr.
And
Howell.
then he like lost like free diving.
Alright.
Mr. Howell. You can feel the pressure in the pool.
Yeah. I said that in the beginning, yeah.
Like, you don't have to go.
No, once you're down like 10 feet, you're good. Absolutely.
A paralyzed guy has to like die because he went to vomit. Yeah, and then he's sure like twice a year. I just went and died one time. Does he know?
It's like a big.
What?
When you can.
There's a guy that was paralyzed.
Uh-huh.
He went diving in the water one day and he came up and he walked. So now he goes, and the deeper he goes, the longer he can walk. So now he only needs a wheelchair.
See, this is the.
Yeah, I find that very, very hard to believe. I'm sorry.
You went 5.
Alright. Let's get back on task. Back on focus. Now, we're going to calculate the pressure exerted by a fluid and calculate how pressure varies with. To do this, we need to discuss what pressure is. Pressure is a measure of how much force is applied over a given area. For example, why when you lay on an acupuncture bed or on a bed of needles or nails, does it not pierce your skin, Reese?
Because it's spread out throughout your body instead of like one place, which is why if you step on a nail, it'll hurt.
If I step on a nail facing up, what's going to happen? It's going to go to my foot. Because all my force, or at least half my force, is coming down right on that nail. Now, if you lay down on a bed of nails, the force of your body or its weight is distributed as a distributed force over that bed of nails. Now, another example. So the pressure changes. Another example. If I'm standing here on 2 feet, the amount of force applied is my weight pushing down. The area is 2 of the bottoms of my shoe. That's the area, right? 2 of my shoes are on the ground, so the cross-sectional area in contact are 2 shoe areas. The minute I do this, what happens to my area? How much area am I now standing on compared to the beginning?
Half.
Exactly. Half. Right? So if this was 2 whatever, this is half of that. Now, if I lift this foot, I notice it's more difficult to stand because I'm increasing my pressure. If I were to try and stand on a tippy toe and like lift up off this foot, it's very difficult to stand because now you're only in a small area. So the pressure is going up a great amount. That's what this formula is telling you. Take a look. Area is in the denominator. So that means that pressure is inversely related to area. Okay? Pressure is inversely related to area. So as the area of contact goes down, you have an increase in pressure. Think about a balloon. You go up to a balloon with a stylus, okay? And I tap the balloon with the stylus. Anything gonna happen?
The sharp stylus?
This stylus.
Oh, that, no.
It'll move.
It'll move, but will it break?
No.
If I
Okay.
do, yeah.
Then I take a needle and I do it very lightly. What's gonna happen? Pops. What's the cross-sectional area of a needle compared to a stylus? Much smaller. So it's a lot more pressure. Awesome. It's a ton more pressure. Okay, not a ton, literally it's 2,000, but a lot more pressure. A lot more pressure over smaller cross-sectional area. All right? Now, the units in these problems Force is measured in newtons. Area is meters squared. The units are called pascals. Pascal was a French mathematician and physicist.
Pascal's triangle.
Yes, Pascal's triangle, named after him as well, a lot more than just this too. He was also a philosopher and an inventor. This guy was a Renaissance man. He did a lot. He came up with this principle we're going to see in a little while, okay, that describes equal pressure in a closed container. Now, how about force and pressure? How are force and pressure related? How are force and pressure related? Look at the formula. Maria?
Isn't like in pressure?
How are they related? As something does this, the other does this. Give me your relationship.
Inversely related.
Okay.
As force increases, the
As force what?
increases.
Increases?
The pressure increases.
Good. So they are directly related. Very good. As force, when I say how they're related, that's the kind of statement I want. As force increases, pressure increases. That makes sense. Think about it. If I push down harder, I'm putting more force. Well, it's also more pressure on the table. There's more pressure on the table. And that's clearly obvious because force is in the numerator, so it must be directly related to pressure. We're going to talk now about atmospheric pressure. Now, the atmosphere around you is really a fluid because it's a gas. The air around me is a combination of gases, thus making it a fluid. If there's a fluid around me, I feel pressure from it. Just like fluids in the pool. Water in the pool, you feel pressure. How come right now I don't feel the atmosphere on me though? Why don't I feel like real pressure like when I'm at the bottom of a pool? I'm used to it. Our bodies have adapted to this. Our bodies have adapted to it. Now,
It's the same thing when you're like, you don't see your nose, but you're actually like there, but you don't see it when you're like looking to the front. You know, like,
You always look at
you know, like,
your
just
you
like-
always look at your nose.
is that right?
You're always-
Yeah, like if you look straight, like look down,
You know, like
look
physically, you're
down.
always.
I get something in your eyes that go up, but it's always there.
Cool. So we're used to it. Good. Now,
Why is everyone else singing?
for, come on, focus. For that reason, we can say that there's the atmospheric pressure always pushing down on us. So for those of you that like to have lame excuses, you could tell your parents that you have a lot of pressure on you right now. All right.
Is that what
And
you
then when they
mean?
say how much pressure, you tell them, well, 1 times 10 to the 5th pascals, clearly.
Pressure doesn't affect you.
That's what like.
Is that what you said to your parents?
Where the pressure is like
That's a
higher,
Pascal.
it's like harder to measure.
It is more difficult to. It's also the air is thin and thicker as you get higher up.
Because that's like.
Elevation changes a
I
lot.
was in
yeah?
Colorado and if I swear to God, you went up the stairs and you got like acrobatic.
No one?
Yeah, the air is much thinner when you're higher elevation, yeah.
That's why it's called mild.
Alright, now, let's move on. Well, hey, the units in this chapter, we're going to use our pascals, but you should know the following. The units of atmospheres are pressures. So if you said 2 atmospheres of pressure, it means double atmospheric pressure. There's also measurements of pressure that can be written in PSI, which are pounds per square inch, focus, which are pounds per square inch. There are units of pressure in what are called millimeters of mercury, which are very rarely used, okay? But we're going to be looking at pascals. But these are all the same thing, they're just like converting from inches to centimeters, okay? So pascals, PSI, atmospheres, millimeters of mercury, they're all units of pressure. We're going to be looking at pascals. Now, Pascal's principle says the following. If a pressure is applied to a fluid in a closed container, it is transmitted equally to every point in the fluid. I'm going to take your iPad away, guys, if you don't stop. I asked you once already. Pressure applied to a fluid in a closed container is transmitted equally to every point in the fluid and to the walls of the container. And this may seem like no big deal, but this is actually an amazing aspect, or amazing theorem. We're going to see how it applies to everyday life in a minute, but a simple example I want you to do tonight, and this is an opportunity for a little bonus. Okay? I'm not telling you how much bonus, because then people may or may not do it. Those who want to do it will, and they'll get bonus. Take an egg when you go home. hold the egg the long way in your hand. So for example,
Oh, you told us this.
I've mentioned this before, but I don't think you did it as a bonus yet, right?
No.
Okay, say the egg is the shape, it's not, but it's clearly an ellipse. So the long shape of the egg, hold this way. Okay? Hold this way. Now, wrap your hand around the egg so that your fingers are pretty evenly distributed around that egg. So kind of spread them out like it looks a little awkward, right? Don't hold it just like this. So wrap your hand around the egg and then try and squeeze it. Try and crush it. Okay? What'll happen is it's not going to break because of Pascal's principle. The pressure you apply gets evenly distributed and it remains in a state of equilibrium.
I can break it.
Now, if you suddenly apply even a little slightly more pressure on one finger, it might break.
No.
So you really need to focus when you do this on applying the same amount of pressure to every finger, which is tough. So you might have to do it more than once, you might get a little yolk. So if you're allergic to yolk, please don't do it.
You're
this
gonna
time.
give us all salmonella.
Now, if you want to get bonus, if you want to get bonus, you need to record it and send it to me. Okay?
Okay.
If it breaks, do it again. Show me again.
Can I
Okay.
just send you a video?
Of you doing this.
So I can send you a video.
Of you doing this.
So I can send you a video.
Stop. Now, so apply as much pressure to that egg as you can, and what you'll notice is it won't break, it'll react, and you'll feel actually a push back. Okay? So try, if it does break, it breaks, you know? But try and get it so it doesn't break. If you're slightly off, then it will break. Either Dropbox the video or quickly add a YouTube link and just send me the link, whatever.
Can you just write it all for one?
It's not homework though, it's bonus.
Yeah.
It'd be like bonus.
Can you email?
All right, I'll say it's due Monday with your egg drop. Do it by next Monday. Okay? So I'll put homework due and I'll add that to the list on the homework due.
So it doesn't break when you stop.
Well, what you'll notice is I want to see, like, when you apply force, you'll see veins in your arm move or you'll see some stress. So I want you to actually be doing it. Don't be like faking it,
Wait.
like,
Wait, what if you always have like really big
When you
veins
just- yeah.
because you're just jacked?
yeah, just show me and make a comment. Be like, that it's not breaking your applying force. You don't have to break it. Guys, it's not like you have to keep doing it until it breaks. Okay? Yeah. So just show me that you've tried it, that you understand it. Alright, I'm not going to answer that. She just asked the same question, I just answered it. Now, an application of this, one that is very, very widely used, are hydraulics. Hydraulics are everywhere. Okay, hydraulics are in pistons, hydraulics are in lifts, hydraulics are in hospital beds. When the hospital beds go and they lift up because the person's in rehab, it's a hydraulic lift that's using that. Okay? It's a hydraulic actuator is usually the word. Now, here's what a hydraulic lift is. A hydraulic lift.
That's a
Yeah.
hydraulic.
Stop. You're really pressing my nerves right now.
I'm sorry. I'm pressuring your
And I-
nerves.
Pressing my nerves.
Was that
A hydraulic lift is an idea where there's a fluid contained in a chamber. And if you apply force to one of the pistons, it lifts the other piston. Now the other piston can have a lot more force on it. So you get what's called the mechanical advantage out of this. For example, if you've ever tried to move an object that's very large onto like a truck, like a moving truck, like a U-Haul, you would use a ramp, you put it on a dolly, and you push it up the ramp. That's a mechanical advantage. You're pushing for a longer distance, but it's not that difficult to do it, although you're still performing the same amount of work. Okay? Same thing is happening here. What happens is this. The force applied F1 does not have to be much of even a fraction of what F2 is. F2 is the weight of the car pushing down. And that's what's pushing down on this side. And it's a reaction pushing back up from this F1. So what happens is you could push down with like 20 newtons of force, and as a result, 2,000 newtons of force are exerted on that car. But here's the difference. The distance you push down over here might be like a full meter, and the car will only go up like a centimeter or 2 centimeters. Same idea as like a jack when you lift up your car. You got a flat tire on the side of the road, there's a mechanical advantage in that jack. You sit there and you keep sitting there and you press the jack every time. What happens is every time you press a full, like say, 7 inches, the car goes up like a 1/10 of an inch. And you keep sitting there pressing that jack over and over, and the car lifts up a little bit at a time. It's a mechanical advantage because you're not applying a lot of force and it's lifting it up, but it's moving up very slowly. Same thing as this. Okay, let's prove it mathematically. Pascal's principle tells me that the pressure exerted on all parts of the fluid and all walls of the closed container is equal. So I could say that this is a pressure here and there's a pressure here. I could say that these are equal. Now, the formula for pressure is force over area. So the pressure at location 1 is force 1 over area 1. The pressure at location 2 is force 2 over area 2. If this is true, then I could say, well, let's figure out what force 1 is in this problem. So I can figure out what the applied force needs to be, so what I have to push down with to lift this car. So go ahead and solve for F1. How do you solve for F1? Multiply both sides by A1. Or simply move A1 up here. So F1 becomes F2. Now I have A1 over A2. I'm going to write it like this. And I'll do this for a reason. Okay, it's the same answer. If I got rid of this A1 and put it up here, okay, this is the exact same answer as this is right here. I'm going to write it as a ratio. The reason I do this is as follows. If the force from car 2 or force 2, whatever this is in this case, is say 5,000 newtons, if I have a ratio of the areas, and clearly area 1 is much less than area 2, look at the diagram. Since area 1 is less than area 2, this is going to be a fraction, right? So if I take a fraction like 1/4 times the weight of the car, it means that the applied force I'm pushing down with only has to be 1/4 of the weight of the car. Maybe 1/10, maybe 1/20. So what we can do is we can vary the cross-sectional areas, and as a result, we don't have to apply as much force. Okay? So what this is saying is that the force applied F1, write this in words, the force applied F1 is a fraction of, that's the A1 over A2, a fraction of the force felt on piston 2. The force applied on location 1 or piston 1 only has to be a fraction of the force felt on the second piston. It's a mechanical advantage. Let's look at an example of this now. Let's take a look at an example of this. Can I get a reader, please? Nice and loud. Go ahead, Nick. Thank you.
In a hydraulic lift, a 550 newton force is exerted on a 1.5 meters squared piston in order to support a weight that's placed on a 4 meter squared piston. How much weight can the wide piston lift? How much pressure is exerted on each piston?
So we've got the exact setup we just had a moment ago. Here's a hydraulic lift. Let's say this is the smaller piston, this is the larger piston. The car is at rest on top of this piston. You're applying a force down on the smaller piston. The force you apply is 550 newtons. The cross-sectional area there is 1.5 square meters. Now we know the cross-sectional area of the car's piston is 4 square meters, but we don't know what F2 is, what the weight from this car could be. We want to find F2. So let's use Pascal's principle. Okay, let's use Pascal's principle. Do you have a hand in the back?
Well, wouldn't you just divide F2?
So let's solve that equation. Yeah, let's do it though, Thomas. So P1 equals P2. So F1 over A1 equals F2 over A2. Now, this time we're solving for F2, not F1. So how do I solve for F2? Yeah, multiply A2 up. Okay, it's the same answer we got previously, but now instead of A1 over A2, it's A2 over A1. This becomes A2 over A1 times F1. So in the previous theoretical example, we solved for F1, the force that you push. But we know what the force is that you push, 550 newtons. We're trying to find the force that the car could have, or the weight of the car, the maximum allowable weight of the car, F2. So we notice that our fraction in the front now is a reciprocal of the fraction we had earlier, because we're solving for the other force. Let's go ahead and plug in now. 4 square meters over 1.5 square meters times 550 newtons. What do you notice about your units of square meters? Isn't that convenient? Why is that convenient? Because force you're getting as an answer is measured in newtons. And 550 has newtons there. The ratio of 4 over 1.5 will always, 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 always be unitless. It could be square inches over square inches. It could be square meters over square meters. It could be square feet over square feet. It could be square centimeters over square centimeters. As long as they're the same, they cancel. So as a result, I get some ratio here, 4 over 1.5. And then I multiply that by 550. This is your mechanical advantage. This ratio. I would jot that down in my notes because that's definitely going to be a multiple choice or theoretical problem. Okay, the mechanical advantage here in this problem is always the ratio. So what does that ratio turn out to be?
1,466.7.
That's your final answer, agreed. But what's that ratio, Scott? Give me the intermediate step. What's 4 over 1.5?
2.66.
All right. So we get 2.6 repeating times 550, which as Scott said was 1466.7 newtons. But the key part is to note that this is your mechanical advantage. And that makes sense. Think for a moment. You push with 500 newtons of force, around 500. You get out 1,500 newtons on the other side. It's almost triple, right? Almost triple, 2.7. So this is pretty crazy to think about that. You don't really need to be able to lift a car in this situation. You need to be able to lift a third of a car, in a sense. Okay, that's your mechanical advantage. Now the last part says to find out what the pressure is on either piston. Well, you know the force and area on the first piston right here. So go ahead and find the pressure. It doesn't matter which pressure I find, because Pascal's principle says the pressure is equal throughout the whole thing. What do you get as a result for your pressure? What do you get as a result? 550 over 1.5?
366.
Point?
666.
Good. Oops, 366. Okay, 366.6 repeating. Around. Why are my units pascals? Pressure, and it's newtons over meters squared, right? Okay, newtons per meter squared.
So always on a test, like let's say you have part B and part A, you could solve for pressure without doing
Sure.
when you did.
You could have done the pressure first, absolutely. Absolutely. Okay? So we have our pressure there, and at the bottom here, we've got our force felt, or force felt by the second piston, which is the maximum allowable weight of the car. Anything more than that, the piston won't lift up. Okay? All right, almost over it, we got it. Now, let's talk about, and we needed that previous part first though. Let's talk about how pressure varies with depth. Okay? Now, the pressure felt by an object under a fluid is really due to the weight of the column of fluid above that object. So do me a favor. Draw the surface of water like this. Draw yourself a box in the water. 3-dimensional. God bless you. Okay, draw a 3-dimensional box. So a rectangular solid. Now, if I were to shine a flashlight from below that box, and imagine the light rays didn't spread out, they just went straight up. The shadow that it would exist on the surface would extend straight up from all the corners. And this shadow that you would see at the top of the surface here is where the box's cross-sectional area is on the top. Agreed? Does that make sense? You shine the flashlight from below. This would be the shadow that would exist. See this channel of red? This box of water? I know it doesn't make sense, but that column or box or pillar of water there, the weight of that water is the force you feel on you. Again, that is the force, the weight of that water. So the pressure that you feel, pressure is force over area, I can replace the force with the weight of that water. But what is the formula for weight? How do you find the gravitational force on an object? What is it? mg. Very good. Stay with me, Mike. We're almost there. What is this? A fluid or an object that's on top? A fluid. So let's call it mf, mass of the fluid. Now, what can I replace mass with from last section? Nick? What is it? Rho v, yeah. That's all right. PV or rho v. I don't want to use P because P is pressure now. So let's make sure we say rho. Rho v. Rho is the density, V is the volume of the fluid. Okay, V is the volume of the fluid. Little geometry for you. Let's do this. How do I find the volume of that red solid? Volume of any rectangular solid?
LW.
Yeah. LWH. The LW part is really that black cross-sectional area that's been shaded in there. But let's replace it in the formula.
So Mr. Allen, in the problem they would tell you like it's 20 feet under. And then
Correct.
Use that as your height.
Yes. And we're going to see in a moment that all we need is the height, so hold off on that. Take a look at the formula now. What cancellation or simplification can I make? What is A in this whole problem? What is A? Area of what?
Of the thing.
That black area shaded in, right? But isn't A the same as LW?
Wait.
Look at A. A is the shaded in rectangle. The area of this rectangle is length times width. I'm being distracted, sorry. Area of this rectangle is length times width. So you can cancel the area in the bottom with LW only, leaving behind our final formula of rho of the fluid, depth or height in this problem, times G. The pressure felt on an object underwater from the fluid only, this is just from the fluid above it, the water above it, is the density of the fluid times the height of the water, which is really the same thing as the depth. If I go down deeper, the height of the water is more. So the height of the water is really depth times gravity. So if the fluid is more dense, if it's mercury instead of water, I feel more pressure, it's heavier. If I go deeper in the water, H increases, more pressure. If I'm on Jupiter, where gravity is stronger, more pressure. This is the pressure felt from only the fluid directly above me. Now, before I go further though, what fluid is above the water? Air. And air exerts what's called atmospheric pressure. So the total pressure is the atmospheric pressure plus, we say rho GH. Okay? So please write a note. This is from the water or fluid that you're submerged in. This is the total from the air above you and the water you're submerged in. P0 is atmospheric pressure. 1 times 10 to the 5 pascals. That is the pressure from the atmosphere always. So no matter what for these problems, you're going to be doing this. Okay, that's always what's going to be happening. Whenever you're finding the total pressure, you're going to take your atmospheric pressure and add it to the pressure you feel from the water. Okay? I'll put water because we are always submerged in water. We're not really going to be submerged in other stuff. If you were in a lab, right, you might be using other fluids. So you use other densities, but I'll say water. Okay, the pressure from the water.
Is it a lot?
Pressure from the water? If you go deeper, it is a lot, yeah. If you're not that deep in the water, no, it's not much. Okay? Let's take a look at an example to see, okay? Let's take a look at an example to see. Please, for this example.
Calculate the depth in the ocean at which the pressure is 3 times atmospheric pressure. The density of seawater is 1,025 kilograms per meter.
Per meters cubed. Calculate the depth. So we're looking for what variable? H. Very good. Now, at which the pressure is 3 times atmospheric pressure. You need to understand how I just wrote that. So listen again if you didn't see it. At which the pressure is 3 times atmospheric pressure.
Is the atmospheric pressure
It's on your formula sheet at the bottom, yep. So we go to our formulas, our formula, and we say the following. Okay, well, the density, don't forget, is 1025. It's given.
Is that G gravity?
That is gravity, yep.
So you make up.
Now, we know what the pressure is. It's triple atmospheric. So replace it with 3 P zeros there. Again, I'm replacing this 3P0 for pressure, because that's the pressure we want to know. We're trying to figure out the depth so that the pressure felt by a person is triple atmospheric. So 3P0 and a P0, they're like terms. So what do? Subtract 1 P0 from both sides, giving me a result of 2 P0 equals rho GH. And what am I looking for, everybody? So divide by rho G. Go ahead and type this in your calculator, please. What do you need around your denominator? Thank you. You need a major set, or else it's not going to work. Figure out the depth at which you would feel triple atmospheric on your body. Right now you're feeling atmospheric pressure. We're trying to find out when is that going to be tripled? How far down do we have to go? What that number is? Yep.
Mr. Howell, I don't get why you took away, why you made it 2
Yeah, wouldn't that give you the double pressure?
No. Again, look, guys, look. You already have atmospheric pressure from the air. You want at least 2 more times that from the water, together giving you triple the atmospheric pressure. Since you're subtracting this P0, it looks like you're looking for double. You're not looking for double. You're looking for when the pressure is triple. You could plug in numbers up here if you want to, by the way. You could type in 3 times 1 times 10 to the 5th, make this 1 times 10 to the 5th, and subtract that way. That works also. That's what Bobby just mentioned. What do we get as an answer here? 19.89. I hear 19.9. Agreed? Check. Units of? Depth. Now, reasonably speaking, how many feet is that approximately? Around 60. It's 3 feet per yard, really, and a yard is close to a meter. So let's say 60 feet. So if you dive down in the water 60 feet, you'll feel triple the pressure on your body that you would normally feel. Okay, if you dive down around 60 feet.
Is it possible to hold your breath for 60 feet?
To get down 60 feet? I'm sure people do it, yeah. I mean, 10 feet is a normal pool in the backyard.
The guy.
So 6 times that. That's not that
The
far.
guy that broke the world record went down 561 feet.
561 feet?
No.
Homework!